doubts and discussions of okay, Ganesh, sheet number 3, question 1. This is from the second set, I guess. Okay. So, okay. So let's turn to sheet 3 from the second set and question number 1. Okay. So this says that the data of the question, why are harmonic modes also called resonant modes? Yeah, because Ganesh, the reason why harmonic modes are also called resonant modes are because if there is resonance, then it occurs at the harmonic frequencies. So resonance का मतलब क्या होता है? Okay, so before we come into this question, let's discuss about resonance in waves. Resonance is when you have waves of a certain frequency created near a medium, okay, that can vibrate in a standing wave pattern. At the exact same frequency. Okay. And as a result, a large amplitude harmonic wave is observed. In other words, what is happening is, for example, suppose we have a spring like this, whose fundamental mode of vibration is 200 hertz. Okay. And what we are doing is we are not plucking the spring directly. We are not giving directly any energy to the spring, but we are creating sound waves around this. Right? We have a tuning fork, which is creating sound waves. So if this tuning fork has a frequency which is, let's say, 600 hertz, or it is 1000 hertz, or any harmonic of this one, or any of the modal, then what will happen if that is the case? So if F matches any of the modal frequencies, then we will see, then it will be observed that the vibration of the tuning fork creates large amplitude vibration of the string. at the same frequency. This process is basically resonance. So resonance can occur, the easy transfer of vibrational energy from one source to another medium without them being in contact. Okay. This phenomena can only occur if the frequency of that source matches one of the harmonic modes or matches one of the modal frequencies of the other one. Okay. That is why it is called resonant modes or harmonic modes. Whereas what will happen is if the frequency of the tuning fork is not equal to any of the resonant frequencies, then there's no resonance. Okay. So in that case, the presence of the vibrating tuning fork will not create any standing wave in the string. Okay, so that is the general idea of resonance. Yeah, the resonance phenomena, Ganesh, occurs because see, that string is capable of vibrating in certain frequencies, wherein what will happen, the pulses of energy that are created back and forth by reflection, they create vibration of the medium particles at that particular frequency. So if the tuning fork around it, okay, is causing the air molecules to vibrate at that particular frequency, then there is easy transfer of energy between the sound waves created in the air molecules and the string, because the sound waves in the air molecules are there. That physical vibration of the air molecules is causing the string to vibrate at the same frequency, and that same frequency is supported by the string in a standing wave pattern. But if the frequency does not match, it does not support in a standing wave pattern. Okay, so there isn't easy transfer of energy in terms of vibrational energy between the air molecules which are vibrating because of the sound created by the tuning fork and the particles of the string which are vibrating in transverse direction. Okay. So it is really about a particular medium has certain modes in which it can vibrate, wherein it creates a stable standing wave pattern. But for it to for it to vibrate in that mode without too much dissipation of energy and with a large amplitude, we need to keep feeding it energy at that same frequency. Otherwise, that energy will dissipate very fast, and we will not get amplitude. We will not get, we will not get a finite amount of amplitude. We get infinitesimal amount of amplitude. So if we want that string to vibrate continuously at a certain frequency without physically directly giving it any energy, like plucking it or something like that, then so basically there are two ways in which we can create standing waves in the string. One is we can directly pluck that string, like you do in a stringed instrument case. Okay. So now what happens in a stringed instrument case is much more complex than what we have discussed in the case of standing waves. A stringed instrument, or any string for that matter, if you directly give it some energy by plucking the string. Okay, so basically by plucking the string, what you've done is you have displaced the string from its natural position. So it has got elongated. So you've given it potential energy and then you released it. So what happens is you have created a pulse by giving it potential energy, but that pulse is very fast going back and forth between the two boundaries as it is continuously reflected. And this series of reflected pulses, they are all superimposing with each other, but they superimpose with each other in such a way that they always have to form a pattern where the two ends are nodes. Alright. Now such a medium will never form a pattern which is only one of the harmonics, like the fundamental or the first overtone or something like that. If you actually take a snapshot picture of a string which is vibrating you will not see that it is in one of the modes of vibration. It will always be in a sort of situation where it is a superposition of all the modes. So it's very, very complicated. So if you plug a string like this, whose fundamental frequency is, let's say, 200 hertz, then it's not actually creating sound of only 200 hertz. It's going to create sound of 200 hertz, 400 hertz, 600 hertz, and so on and so forth. Because it's vibrating in a very complex pattern, which is a combination of all these frequencies. In principle, if you wanted to vibrate exactly at 200 hertz, what you would have to do is you have to plug it exactly at the midpoint and release it, so that the midpoint has to be an antinode. But even that is physically impossible, because there is the whole concept of error. You cannot exactly find the midpoint of a string. You will always find a point where there is some bit of error compared to the exact midpoint. So no matter how hard you try, if you plug the string, it will always vibrate in a very complex combination of its fundamental and overtones. And that is why the sound it creates, it always has what we call the pitch. When we discuss about sound, I'll discuss in more detail the difference between pitch and frequency. Frequency is a simple, is a single term, wherein the vibration is happening at so many cycles per second. Pitch is a sound that is created when you have sound which is a complex combination of frequencies, but those frequencies are related to each other by harmonics. And when they are related to each other by harmonics, so when I create a sound where there are multiple frequencies, but the frequencies are are numerically related to each other. So the sound is created such that you are hearing, the vibrations are happening at a frequency of 200 hertz, 400 hertz, 600 hertz, and so on and so forth. Then that sound appears to be musical. It appears to be like a musical note whose pitch you can recognize. Whereas when we create noise, like when we drop something on the floor or some machinery kind of noise, then there is no musicality to the sound, and that occurs because there is sound created of different frequencies, but those frequencies are not related to each other harmonically. So if you talk about let's say the intensity of sound created. Now I'm going forward into sound in this discussion, but we will come back to this later again. So if the intensity versus frequency is like this, that you are hearing the intensity at a certain frequency, at a certain other frequency, at a certain other frequency, and these frequencies are all related to each other harmonically, then this appears to be a musical kind of sound. It has what we call, it has a pitch and it has a timbre. It has these two qualities, which we'll discuss more in detail. Whereas if you hear a sound which is such that the intensity versus frequency is more or less like this, so it's a continuous set of frequencies, then this is noise. Like you would have heard the term white noise. White noise consists of all frequencies which are equally present. Okay. So now coming back to this, whenever we plug the string, we never get, like we discussed last time, that there are the different modes which are possible. Like the fundamental frequency is 200 hertz. The first overtone might be 400 hertz and things like that. So we will never get a sound from the plugging of that string. So this time I'm not talking about the tuning fork. I'm just saying you have the string alone. Okay. And if we plug it, we are not going to get a sound of a single frequency. We'll actually get a pattern like this. Yes, typically speaking, the fundamental frequency will be present at highest intensity. So it is most dominant. But along with that, there will be other frequencies which are the overtones also present. Because the string will actually be vibrating, which is in a complex combination of this. It will be vibrating in a pattern which looks like all of these things are happening together. So if you write an equation, we have written the equation for each of the overtones. Now, if you write an equation where all of them are superimposed but with different amplitudes, the resultant wave pattern that you will get, that is the actual kind of vibration which is happening. It's extremely complex. So for that matter, if around near the vibrating string, you were to put a frequency detector which detects the frequency of sound heard, it would show you this kind of data. It would not show you the data that is vibrating at one particular thing. Yes, you can find such. In fact, Fourier transformation, I will discuss about it in, in a bit of time today. But Fourier transformation is all about this only. When a sound is created or a wave is created, which is a combination of frequencies, that itself is Fourier transformation. Okay. And any kind, so Fourier transformation basically says that any wave pattern is nothing but the combination of many frequencies. So such a wave pattern can even be a non-periodic kind of wave, but even then it can be written as a combination of periodic sinusoidal waves. Actually, okay, so that's a very interesting thing we'll discuss about. Okay, now coming back to this thing, so the difference between resonance and a string vibrating on its own in a combination of these frequencies is that in resonance, what happens is that the string will vibrate at a particular frequency. Okay. So resonance is that kind of phenomena wherein, like, suppose one of the common things in resonance is that if you have a piece of machinery which is creating a lot of noise, but that noise consists of many frequencies, and you bring a stringed instrument near that machinery, then it is quite possible that the string will suddenly start vibrating. Or if you have like a metal part in that machinery, like you have the mudguard of a bicycle, or you have like you have a metallic door of a car which is slightly loose. So if it is slightly loose, it might be capable of vibrating. Now when the car is moving at a particular speed, you will see that that door will start vibrating violently. Or if the bonnet of the car is loose at a particular amount of acceleration, that bonnet might vibrate a lot. Whereas you increase the acceleration further or decrease the acceleration, the bonnet stops vibrating. So that again happens because of the phenomena of resonance. Because the engine is creating vibrations at a combination of many frequencies. But if one of those frequencies happens to match one of the resonance modes in which another part of the engine can vibrate, like that metallic bonnet or something, then it can create resonance wherein that bonnet will start absorbing energy from the waves created by the different vibrating parts, and it start vibrating with a large amplitude. So that phenomena is called resonance in wave mechanics. So broadly speaking, in wave mechanics, we say resonance is when you have a source of waves whose frequency of vibration matches the one of the harmonic modes of another medium, and that source may not be in directly contact with that medium, but just the fact that it is creating vibrations of a frequency which is matching one of the harmonic modes of the other medium, that creates an easy transfer of energy between them, and you observe the phenomena of high amplitude waves created in the medium, and that is called resonance. Okay, so Somadeep and Ganesh, hope this point is clear to both of you. Yeah, so if you draw a graph between amplitude and external frequency, the frequency corresponding to the maxima is the resonant frequency. Yeah, I mean, if you were to do this, like, if you had some mechanism where instead of this being a tuning fork, this is a general, let's say, electronic kind of, vibration generator. So you can keep changing the frequency continuously. So you keep changing the frequency continuously, and you observe the amplitude of vibrations created in the string. So you will see that at certain frequencies you will get amplitude, and at the vast majority of other frequencies you will not get any amplitude. So those frequencies will become nothing but those frequencies represent nothing but the harmonic modes. That is correct. Yes. All right. Now Fourier transform is something very interesting, and I will actually send you guys some videos which explains Fourier transform more geometrically rather than mathematically. But the whole idea of Fourier transformation is a system in mathematics wherein basically any any wave phenomena, let's say we are talking about this thing, transverse vibrations, it can be treated as a summation of sinusoidal waves. This is the basic idea of Fourier transform. And this could be literally anything. This could be a periodic wave, or it could be a non-periodic pulse also. Anything can be treated like this. So we'll see a few examples. For example, if we have, let us say, okay, suppose we have this phenomenon. Suppose we have a wave which is a superposition of two waves, where you can see that this first wave has amplitude 4. It has frequency equal to 3 by 2 hertz. And it has lambda equal to 4 centimeters or whatever that is. Okay. And the second one has amplitude equal to 2, but it has lambda equal to 8 centimeters and a frequency equal to 3 by 4 hertz. Now, if I ask you, okay, draw the graph of y versus p at x equal to 0, and plot the snapshot of y versus x at t equal to 0. Yes, I'm coming to that, Ganesh. It's a very interesting phenomenon. Okay, but let's start with this one, and we'll understand more about it. Okay, so let's try this. Okay, this one is pretty easy. You can understand this by simple trigonometry kind of thing also, okay, or maxima minima concept also. So try this out. Okay, plot the graph of y versus t at x equal to 0. So that will tell you that any particular medium particle, like the one at x equal to 0, what it is doing with respect to time. So it will show you the type of periodic motion it is undergoing. It's a combination of two periodic motions. So obviously it's periodic. So Ganesh, I will come to your point, okay, that yes, any arbitrary wave, like even an exponential pulse, forget an exponential pulse, even a very arbitrary pulse that you're drawing. Like even if you draw a pulse which looks like a square pulse like this, even that can be shown as a combination of sine waves. A single square pulse like this also can be drawn like a combination of sine waves. This single square wave, moving like this, it's a very, very complex series it will be, but it can be shown as a sum of sine waves. Okay, so let's start with the first part. First part, y at x equal to 0 will become minus 4 sine 3 pi t minus 2 sine 3 pi by 2 t. Okay. So we want to understand how this will exactly look like. We can find For example, one way we can interpret this is we can write this as or we can leave it like this, whatever. But so now we can apply maximum minimum on this. Because we can understand that it is a periodic function with a time period of how much? A time period which will be this one has a time period of 3/2 seconds, and this one has a time period of 3/4 seconds. So anyway, so if we were to differentiate it, the derivative of this would be okay. So we just calculate the maximum minimum for me in this. We can do a simpler job of calculating the maximum minimum. We can just write this as y is equal to -2 into 2 sine 2 theta plus sine theta, and see how we get the maximum minimum of this. So derivative of y Yeah, but the whole point is, when there are multiples, that's when it becomes really interesting. Okay, let's try a simpler one. Let's try one where this one is cos and that one is sine. Okay. So suppose we had something like this. Suppose we had something like, so we are the this is at x equal to 0. So suppose we had something like this. So we would see what kind of pattern we would get over here. So to understand that, this is like something like this. So sine theta is 0 would give us derivative is 0, or cos theta is 1 by 8. Okay. So we would see that at cos theta equal to 1 by 8, okay, what would happen is y's value, and at sine theta equal to 0, what would y become? So this is theta equal to 0, pi, 2 pi, etc. Y would become, or just put theta equal to 0 over here, it would become 2. Is at pi, it would become minus 2. So it would be 2 only. Okay. So y would be equal to 2. Whereas at cos theta equal to 1 by 8, y would become how much? Y would become 2 into cos square theta. So that is 1 by 64. Just a moment, guys. Just a moment. I have to start my white screen again. Yeah. So at cos theta equal to 1 by 8, y would become how much? 2 cos 2 theta. So cos 2 theta can be written as cos square theta minus 1. I mean 2 cos square theta minus 1. So 2 cos square theta would give me 1 by 32, okay, minus 1, plus sine theta would become root of 1 minus cos square theta. So that would become root of, it would be nearly 1, root of 63 by 8, something like this. Okay. हाँ तो वही किया ना. So that is what I've done. The derivative is this. Okay. Oh, plus cos. Okay. Minus. Yeah, minus. Wait. We'll come back to this. cos theta. So yeah, we get cos theta into 1 minus eat sine theta. Alright, is correct now? Okay. So y prime would be 0 for cos theta equal to 0, or theta equal to pi by 2, 3 pi by 2, like that. Okay. Or sine theta equal to 1 by 8. Now every time sine theta is 1 by 8, so let's go back here. So the function was function was 2 cos 2 theta plus sine 2 theta. This was the function. So every time cos theta becomes 0, sine theta is either plus 1 or minus 1. So that means every time cos theta is 0, y is either plus or minus 1. So these are some local maxima and minima. Okay. And every time sine theta is 1 by 8, what about cos 2 theta? Cos 2 theta will become 1 minus 2 sine square theta. So it will become 1 minus 1 by 32. So 31 by 32. Okay. So this will become 2 times that. So that is 31 by 16 plus 1 by 8. So that is 33 by 16. Correct? Which is nearly 2. Understanding? So if you want to plot this graph, you want to plot the graph of cos 2 theta plus sine theta between zero to 2 pi, let's say. So what is going to happen is sine inverse 1 by 8 is going to be like a local maxima point. Okay. And okay. So basically you will have quite a complex kind of graph. You probably have a graph which at 0 you can see the value is 2. So it's going from 2 to a value which is slightly greater than 2. Then you are coming to the point pi by 2 where it comes to 1. Then it's going to again increase. Then it's going to come to minus 1. So you'll probably have a graph which is something like this. So this is where your 2 pi would be at. This would be your 33 by 16, that point, which is slightly greater than 2. So you would observe that your graph would be something very complex like this. So basically what happens is that if for example you took a graph of sine theta plus sine 2 theta, plus sine 3 theta. Now you would get a graph which is even more complicated. You would get a graph which is something like this. You can look up some of these graphs on the internet and all that, and you will see. Okay. So like that, what happens is that Fourier transform concept says that when we write anything as this combination, one very interesting result it tells us is that if the series, that is they are harmonically related, okay, that means that they are multiples of each other, then this represents a periodic wave. Okay. In other words, if we were to plot a graph of E1 sine theta plus E2 sine, let's say 2 theta plus E3 sine 3 theta, this type of graph, or we were to plot a graph of, say, this. Any such graph where the different, so each of the thetas here, are like that kx minus omega t kind of term, but they are related to each other harmonically. Okay, so these would all represent periodic functions. Okay, whereas if the different omegas are non-harmonic, okay, in that function, so remember, so they represent frequencies which are not harmonically related. Okay. So omega is 2 pi f. So the combination of frequencies is such that it's not of this type. So the frequencies could be just random, 200 hertz, then 201 hertz, then 207 hertz, then 219 hertz. So no particular order. Okay, so if that happens, in that case, this represents a non-periodic pulse. So that's another outcome that comes from Fourier transform concept, that you can write literally any shape or any function or any graph as a combination of sine waves. So in very simple terms, what Fourier transform tells us that if we have a graph of y versus x, for example, any graph of y versus x, this graph of y as a function of x can be written as a summation of this. Okay. Now, if the k's over here are harmonically related, then y versus x will be a periodic function. If they are not harmonically related, it will be a non-periodic function. That is the simple concept of Fourier transform. Okay. Now, the mathematics behind it is a little bit more complicated. Okay. And I will send you some very interesting videos from YouTube, which will help you understand this more. And this is what is used in engineering further. So anyway, hope this general idea of Fourier transform is clear to you guys. Yes, Ganesh and Somodeep. All right, so let's come back to the question we were going to discuss. It was from sheet 3, question number 1. So it says that a transverse harmonic wave of amplitude 0.01 meter is generated at one end of a string of a long horizontal string by a tuning fork of frequency 500 hertz. Okay, so the amplitude that is created is 0.01 meter at one end of the string. So let's say that end is x equal to 0. Okay, at a frequency of 500 hertz. At a given instant of time, the displacement of the particle, so y of the particle at x equal to 0.1 meter at some given instant of time is minus 0.005 meter. Okay, so it is minus 0.005 meters, or you can see it as minus a by 2. And at that same instant, of time, the particle which is at x equal to 0.2 meters is having a displacement of plus 0.005 meters, or you can say plus e by 2. So calculate the wavelength, wave speed, obtain the equation. So basically we have to find out phi also, given that wave is traveling along the positive x direction and x equal to 0 is at, so y at x equal to 0, t equal to 0 is 0. It's at the equilibrium position. So given all this information. Okay, so basically see what this information will give us. From this we will get the wavelength. How we'll get the wavelength, let's understand. So see what happens is, if you draw a snapshot picture of a sine wave at any instant of time, so let's say at any instant of time we have drawn a snapshot picture at some particular instant of time. Now let's identify two consecutive particles, closest two particles, which are at plus a by 2 and minus a by 2. So if this one is x1 and this one is x2, this distance between them, how much is this distance in terms of lambda? That is the main thing over here that we have to understand. Okay, what is the relationship of this distance with respect to lambda? Now the easiest way to understand that relationship is compare this graph with a graph of sine theta. If you look at a standard graph of y is equal to sine theta, and you look at 0.5 and minus 0.5. So what is the angle at this point? It is pi minus pi by 6. So if this angle is theta 1 and this angle is theta 2, how much is theta 1? Theta 1 is pi minus pi by 6 or 5 pi by 6, and theta 2 is pi plus pi by 6. So it is 7 pi by 6. So what is the difference in these angles? Theta 2 minus theta 1 is equal to pi by 3. Right? So here what should happen is that kx2 minus x1 should be equal to pi by 3. Understanding the point? And in the question, this point was given to us as point 1, and this point was given to us as point 2. So x1 is 0.1 meters, x2 is 0.2 meters. So 2 pi by lambda into the distance between them, which is 0.2 minus 0.1, that is equal to pi by 3. So lambda कितना जा रहा है मेरे पास? Lambda is coming to be 0.6. Okay, meters. Okay, let me check the question again. What about the other things? Are the wave speed etc. coming correct, or are they also coming wrong? All are different. Okay, so they are corresponding to this. No? Okay. Now, only one thing here is that suppose these points are these ones, then what happens? We are assuming consecutive points. Actually, there's no hint given in the question whether they are consecutive points or not. Okay. Now, what happens if they are these 2 points, for example? Then our answer will change now. Though the question should actually give some hint. Understanding? So this point here, let's say theta 3 would be how much? It would be 2 pi minus pi by 6. So it would be 11 pi by 6. Okay. So 11 pi by 6 minus see, this would give us pi now. So, if, for example, this point, x3, if we take x3 as 0.2 and we take x1 in my diagram as 0.1, okay, then you will be getting that. Then you will be getting lambda by 2 as 0.1. But the thing is, the question should give you a hint. Without that information, so what happens here is, without any information given, there are multiple possible answers. You understanding my point? Without any hint given that whether they are the closest 2 points like this or that, then not only this answer is correct, 0.6 bhi ho sakta tha, 0.2 bhi ho sakta tha. It could also be a case where x1 is this point and the other point is this one. So happen also. So in that case, the wavelength is much smaller than 0.2 also. So I think there is some information missing in the question, and it is like, they are the next to the next nearest. Yeah, there are infinite possible answers, but the question, if you want the answer to be 0.6, it should say that these are the nearest 2 points which are having displacements of minus a by 2 and plus a by 2. And if you want the answer to be 0.2, you should say they are the next nearest points, like that. Okay. So hope the point of the question is clear to both of you, Somadeep and Ganesh. Is Somadeep, is it clear, beta? So somehow this question assumed that you should take x1 and you should take point 1 and point 2 as x1 and x3 in my diagram, but that was not communicated properly in the question. Okay, so the way you have done is correct. If I also read the question, I would have assumed they are the consecutive points, so I would have taken the answer as 0.6. Okay, next, anything else, people? Next doubt. Sheet number 2, question 4. Okay, let me come to that. Variable mass per unit length. Okay. So this question is just a little bit about application of calculus. So here it is given to us that we have situation like this. Now, variable mass per unit length, actually we should write it as mu, whatever, is m naught x. Okay, where x is the distance of a point from the ceiling. So x is the distance from the point from the lower end, and the total length is m naught. Small transverse disturbances, so you have to calculate the time difference. So as this is traveling, you can see that the wave speed with which it is traveling is square root t by mu. So first of all, we have to find the tension at any point. Okay. So what we'll have to do here is at a point like this, which is at a distance x, find the tension at the point P first. Then from that you find the wave speed at the point P, and then you integrate that. Okay. So tension निकालने के लिए क्या करेंगे? We have to first this thing, take this section and calculate its mass. So for that section, you take a differential element dx, which is at a distance x. So that is having mass of mu dx. So that is m naught x dx. So then the mass of that portion up to that point P is going to be integration of m naught x dx, integrated from x equal to 0 to x equal to x. So the mass of that portion is going to be m naught x square by 2. So you can now see from that the tension at that point will become the mass of that much portion into g. Okay. So what I'm saying here is this portion's mass. This portion's mass is, which I've calculated here. So that is m naught x square by 2 g. So now as your pulse is traveling through that point, if the pulse is over here, at that moment its instantaneous velocity at the point P is going to be square root of tension at that point P divided by mu at that point P. So tension is m naught x square g by 2, and this is m naught x. This becomes gx by 2. Okay. So that is your dx by dt. So now something like this you should be getting. Right, Bhaumik, is this clear? Good. Okay, next, any other question, madam, from the worksheets? Sushruth, sheet number 1, question 6. Okay. So why? So this is the snapshot. This is the displacement of the point x equal to 0 as a function of time. Whereas, so now what is happening? The disturbance is propagating. This is moving along positive x axis at 2 centimeters per second. Okay. All right. So basically, this is telling us that it should be a function of, let's say, such that that is this one, which is given to us. Okay. So to convert this into a function which is changing with x, now what we have to do is we have to replace t with this point. Okay. So y as a function of xt will now become like that. It was 2t, so it will become 2 times t minus x by v for t minus x by v being between 0 and 2. And it was 6 minus t. So 6 minus 4 this will be our wave function. it is something like this, that like we had done the basic derivation, that if we were to plot, but this is the way to do the question at the exam level. Okay, this is the way to convert this function of time, where x is 0, into a moving function. You have to replace the t with something which is a function of t and x, such that it's moving along the x-axis. So you have to replace t with this t minus x by v, because x by v has the same dimension as time. Okay. Now the logic of doing this, I'll explain to you how we do this. Okay. So the logic of this is that if we were to plot y versus t at x equal to 0, how that was looking. That was looking like this graph between between 0 and 2. It's a linear function of slope 2. And then 6 minus t. So this is how this graph is looking at the point x equal to 0. So that means the point x equal to 0 is going to go to a displacement of 4 from 0 to 2. Okay. And then come back from 4 to 0 in the next 2 seconds, while all other times is going to remain at rest. Okay. So if we were to convert this into a y versus x graph, okay, how would that look? So if we were to convert this to a y versus x graph, that would look similar, but in such a way that this is now a traveling function. So in this graph, we can see that at t equal to 0, which point is having the peak? Okay. At t equal to 0, a point behind this would be having the peak. So basically, x equal to 0 is reaching the peak at which time? At 2 seconds. So basically, this is what the snapshot picture would look like at t equal to 2 seconds. Okay. Then by the time you want to t equal to, for example, 4 seconds, this is traveling like this. So it should actually be a mirror image of this now. Okay, so at t equal to 2 seconds, the peak is here. At x equal to 0, for example, at 0 seconds, it would have been like this. Then at 4 seconds, it would be like this. And like this is traveling. This is generally at some time t. So this is what this graph would represent actually. This is what this graph would represent. You can see that if you were to put t equal to 0, the graph I would get is exactly the shape that I've drawn at t equal to 0, this triangle over here. If you put t equal to 2, the shape I would get Ganesh, the graph is somewhat different because at t equal to 0, it is at 2. No, at t equal to 0, okay, so see what is happening to the point at x equal to 0. Let's understand that now. The point at x equal to 0, at t equal to 0, it is at 0. Then in 2 seconds, it's coming to 4. And then in 6 seconds, it's coming back to 0. So that's what's happening here. You can see here, no? The point at x equal to 0 is at 0 at this point of time, t equal to 0. Okay. Then by the time it's 2 seconds, it's come up to plus 2. Okay. Then by the time, understood now? So that's how you will see that it's like a reverse of that one. Why it's a mirror image of that one, you'll also understand if you just plot this at a snapshot time. If you were to plot this at, for example, as a function of x, but at t equal to 2 seconds, for example, if you were to plot, okay, or at t equal to 0, or any of these, you will get these corresponding graphs. Okay. So by the time it is 6 seconds, for example, again it's come back to 0. This is how the snapshot will look at 6 seconds. Okay. So that is automatically showing. This is just to show you the fundamentals, but basically the moment you replace t with t minus x by v, your wave is traveling along this direction with v. Okay. So Sushruth, hope this process is clear. So just let me summarize what we are doing. Then we'll come to the exact answer of the question also, because we haven't come to that yet. So basically, see, if I'm given this is some kind of function of time. Okay. So from that, how to get this? This is the idea. No? So what is happening is that this would have been a function of kx minus omega t, like this. And in this, I would have put the value of x equal to x naught, and I would have got this. Okay. So that is the same thing as saying that this. Okay. In this, So basically, whatever function of time you had, you replace t with this, and it becomes this function. Okay, just like, if we had y is a function of x at t equal to 0. Now in this, if you replace x with, it becomes a traveling function. It becomes like that. So that is the idea. Okay. So if you are given a function at x equal to 0 of time, it is basically f of some omega t kind of thing, because the argument of the function has to be dimensionless. So in this, you replace t with either t plus x by v or minus x by v, depending on which direction it's traveling. And from that, instead of a function of time, it becomes a function of a wave. So it becomes this. Similarly, if you are given this, it's basically this type of function. So in this, replace x with x plus minus vt. So it becomes a traveling function. It becomes this. So that is the idea over here. So once we've understood that, so coming back to that question, now we've got this wave equation from that original function that was given. And from that, now we have to just answer the question that, what is the exact question? We have to find the value of the displacement of the particle at x equal to 4 centimeters at t equal to 5 seconds. So, you can think of it like this now. So you can think of a function like this now, that y is equal to 2 theta when theta is between 0 and 2, and it is 6 minus theta when theta is between 2 and 4. And in this, theta is basically what? It is t minus x by v, and v was given to us as 2 centimeters per second. So if we take x in centimeters, so t is in seconds, x is in centimeters. Okay. Now we have to substitute x equal to 4 centimeters and t equal to 5 seconds. So at this value, theta will become how much? It will become 5 minus 4 by 2. It will become 3. So if theta is equal to 3, how much is y? Substitute that here. So y will become, so theta is 3 is coming in the second category between 2 and 4. So it will become 6 minus 3. That will become 3. So y will be equal to 3 at this time. This will be the value of y at x equal to 4 centimeters, t equal to 5 seconds. Now, interestingly, the same thing you can get by the graph also, but it's a little bit more complicated. You will have to, so this graph that I had drawn at t equal to 2 seconds here, it was here, t equal to 0, it was here. So if you plot this graph exactly at t equal to 5 seconds, you can actually see where this would have gone. And from the graph also, from the slope and all that, you can figure out why this will be 3. So that's another something that you people can do. Okay, you can also try to do this by graph. So try to solve by graph. Okay, so just see where this triangle moves by the time you are at 5 seconds, and from that also you can figure out. Okay. Anyway, so let's come to the next question then. Anything else? Okay, let's do one thing then. Let's take a 5-minute break, and then we'll discuss something more about standing waves. Okay, there are some more patterns of standing waves that we'll discuss. Last time we discussed about the most basic type of standing wave, where both the boundaries are rigid. But there are also numerous other types of standing waves, and yeah, almost completed, Ganesh. We just have to discuss a few more cases of standing waves. You're completed to the point where you can solve mains level questions fully. But for advanced level questions in standing waves, a couple of more cases have to be discussed. Okay. So let's take a 5-minute break and we'll come back to that then. Okay. Okay, people. So let's resume. Also, for some reason, I had forgotten to send you guys the recording and the notes from the last lecture, number 7. So I've just sent it on the groups. So let's pick up from standing waves where we were discussing last time. So resonant modes of vibration of a string. The different kind of possibilities. So we had discussed about case 1 last time, where the string is rigidly attached at both the ends. If both boundaries are fixed, then we saw that the fundamental mode looks something like this. When the fundamental mode lambda naught becomes twice the length, and the fundamental frequency becomes this. Similarly, in the first overtone, the shape of the string will be something like this. And we have lambda is equal to L. So frequency becomes 2 times F naught, or like this. And like that, we saw that in the nth overtone mode, frequency, or the general formula of frequency becomes n plus 1 upon 2L square root T by V. So this series of frequencies, F0, F1, F2, F3, like this, they are called the resonant modes. And in this particular case, the formula is that the nth overtone mode has a frequency which is equal to n plus 1th. N plus 1th harmonic of the fundamental. So this was the formula whenever we have this situation that the string has rigid boundaries at the two ends. Okay, so this was the important takeaway from last time's thing. Okay, and apart from this, a few other points which I'd like to stress on again is the concept of also understand that as a string like this is vibrating, in some particular mode, at some instant of time, let's say it's like this, at some time t equal to t. So if you look at particles like this, x1, x2, x3, x4, etc., you can see that x1 and x2 are in SHM in phase. That is, they have zero phase difference. They may have variable amplitude. Amplitudes may be different. Okay, but they will be in phase. They will be okay. Why? Because these two particles are between consecutive nodes. So this is a node, this is a node, this is another node. Okay. So similarly, x3 and x4 are also going to be in phase. They are also in phase. Okay, because again they are between consecutive nodes. But if you look at x2 and x3, okay, or x1 and x3, or x1 and x4, okay, this is a pair of particles on either side of a node. Okay, one is to the right, the other is to the left. So what we'll observe about them is that they are in opposite phase. That is, they have a phase difference of pi. And obviously they have different amplitudes. So this is the next important thing to understand. That if you're looking at the vibration of various particles together, you can see that any pair of particles, if you compare their phase, either they are in phase or they're going to have a phase difference of pi. Only two possibilities are there. Okay. Now, if the two particles in consideration are between two nodes, then definitely they'll be in phase. If they are on either side of a particular node, again they will be in opposite phase. Okay. Achha, another thing is, if between two particles there are two nodes, again they'll be in phase. So for example, this particle x5, now we can see x1 and x5 are again in phase. So there's an even number of nodes between them. There are two nodes between them. But for example, now you see a particle over here, x6. So x1 and x6 will be in opposite phase. So it's like this, you know. So if two particles are separated by 0 nodes or even number of nodes, then they will be in phase. And if they are separated by 1 node or odd number of nodes, they will be out of phase or opposite phase. So you can just make a note of this point. Or, you know, for example, you can get a question like this, that the length of the string is, let us say, 30 centimeters, okay, and it's vibrating in, let's say, it's fifth overtone. Okay, so find the phase difference between particles at x equal to 1 and x equal to 10 centimeters. X equal to 2 and x equal to 14 centimeters. Okay, so just based on this concept, try this out. So the length of the particular string is 30 centimeters and it is vibrating in the fifth overtone, and obviously assume that this is for a string fixed at both ends. So it's this type of diagram, only it's vibrating in the fifth overtone mode. So find the phase difference between the particles which are at x equal to 1 and 10 centimeters from any one end, and x equal to 2 and 14 centimeters from any one end. So for this type of question, there's only two possibilities, 0 or pi. And of course, there's a third possibility that one of the particles is actually a node. So in that case, that particle is not moving. So then there's no question of phase difference. Okay, so there's also that third possibility. But if the two particles in consideration are having amplitude, they are vibrating, they're not nodes, then they can only have either phase difference of 0 or phase difference of pi. So just work out the shape. Yeah, Ganesh, for the first one, 1 and 10 centimeters, is it? Okay, correct. Zero for the second, yes, good. Okay. So the easiest way to do this type of question will be to understand that for L equal to 30 centimeters, okay, in the fundamental mode, lambda will be equal to 60 centimeters, okay, or lambda naught by 2 will be equal to 30 centimeters. In the first overtone, lambda will be equal to 30 centimeters, or lambda 1 by 2 will be 15 centimeters, like that. In the fifth overtone, okay, lambda will be equal to how much? 10 centimeters, or lambda by 2. Why I'm taking lambda by 2 is because that's the size of a loop. Okay, lambda by 2 is distance between consecutive nodes. That is important. Okay. So basically, in your fifth overtone, your string will look like it has 6 loops. Okay. And each of these nodes will be 5. Yes, correct. Okay. So for the first part, we are considering a particle at x equal to 1 and x equal to 10. There is no particular relation because the particle at x equal to 10 is a node. Okay, so the question actually doesn't make sense for that. Okay, so the answer should become that it does not really exist. There is no phase difference that exists because that particle is not vibrating only. Okay, but between 2 and 14, let us understand now. So the particle at 2 is somewhere here, and the particle at 14 is somewhere here. So you'll see they'll be in phase. They vibrate in phase. But another thing you can see, they will have different amplitudes. Okay. You will also see that the particle at x equal to 2 will have larger amplitude compared to the particle at x equal to 14, because x equal to 14 is 2 centimeters away from this thing. No, it is 1.5 centimeters away from a antinode, whereas this is 0.5 centimeters from the antinode. Okay. So it will have larger amplitude compared to the particle at x equal to 14 centimeters. Now, in the same question, another thing that can be asked, for example, is that for the same data, L equal to 30 centimeters, vibrating in fifth overtone. Okay. Now, this next question, for a particle at x equal to, let us say, 15 centimeters, when is the energy density at the position of the particle maximum, and what type of energy is this? Now, given that, assume at t equal to 0, okay, the particle, the string was at mean position. Okay. So that's one thing given. And this quantity is equal to, let us say, 100 hertz. And d for the particle at x equal to 17.5 centimeters. Repeat the above analysis. That is of part C. I'm just minimizing the question. Now, these are slightly more technical type of questions. So just pay attention to what we discussed last time, the redistribution of energy. Yes, very good, Ganesh, that's correct. It will be in the form of potential energy. And it will be at the time when all the particles reach the maximum displacement. So if at t equal to 0, it started from the mean position. So maximum displacement will be at what time? Quarter of a time period, 3/4 of a time period, 5/4 of a time period, that kind of situation. So here time period will be 1/100th of a second or 10 milliseconds. So 2.5 milliseconds, 7.5 milliseconds, those kind of multiples. Yes, what about the next part, 17.5 centimeters? So we'll see that at t equal to 0, if the string is starting from the position like this, then this will be at t by 4, and then it's back to this position at t by 2, and then it's this kind of position at 3t by 4, and so on and so forth. It vibrates like this. So capital T here is 10 milliseconds, because the frequency was 100 hertz. So now if you're looking at the particle which is at uh, what was the first one, 15. So this is when it has maximum energy, and at this point of time its energy is 0. Whereas if you look at the particle at 17.5, it has maximum kinetic energy at this point of time, and by the time it's here, kinetic energy is 0. Okay. Then my diagrams are not consistent. So in this diagram 17.5 is here. So anyway, this would have, so you can see that for the particles at x equal to 15 centimeters is the node, maximum energy in the form of maximum potential energy at t equal to t by 4, 3t by 4, 5t by 4, or so that is this. Whereas for the particles at x equal to 17.5 centimeters, which is an antinode, the maximum energy is in the form of maximum kinetic energy. That will occur when they are at mean position. That is these kind of multiples. Okay, so this is another typical type of question to do with the energy distribution. Okay. Last time we had also seen that the total mechanical energy was given by that formula 1 by 4 maximum amplitude square omega square into mu n is total mass. E max is the amplitude at the antinodes. Right, so hope this analysis and this question is clear to all of you. All right, people. Now coming to only nodes and antinodes can have zero energy. Yes, exactly. Because what will happen is that for example, if you look at a point which is between an antinode and a node, such a point. Okay. Now, when it is at the extreme position, this point is having zero stretch. So, its speed भी zero है, so kinetic energy भी zero है, but elastic potential energy भी zero है. But this kind of a point is having some elastic potential energy. Its potential energy is not zero. Okay, and of course, this sort of point is having potential energy maximum. Similarly, when everything is at the mean position, and obviously only the node is having kinetic energy zero. Everything else is having kinetic energy. So it is only the nodal points and antinodal points which have exactly zero energy at instants of time. So you know what is happening is that if you look at an antinode and a node, if you look at these pairs of particles, so at this moment, all the energy is here. So the energy is concentrated here and now next moment, I mean next quarter time period later, the string is going to go into this shape. Okay. So by that time that happens, what has happened is that this energy has got distributed here and here. This energy has got distributed here and at the next position. So the energy keeps, here the energy is going in this direction. This energy is going in this direction. Now it's come here, so it's going to again go in this direction. Yes, that's correct, Ganesh. So except for the particular points which are at antinodes and nodes, no other points will have zero energy at any instant of time. And also the energy keeps oscillating between the nodes and antinodes. So there's a nice analogy of this given in Resnick-Halliday. So that analogy is like this, that if you have a system which is like this, you have spring mass, spring like this. Okay. And what you've done is at t equal to 0, you've given these opposite velocities. Okay. So what will happen after some time is this. So now the energy is contained here. Energy is contained here. Okay. Then again it comes to this position. but this time this will be on the way down and this one will be on the way up. Again it will go to the opposite position now. So again now the energy is contained here. So this energy keeps backing and forthing between the springs and the masses. So like that over here, the energy keeps backing and forthing between the nodes and antinodes. So it is the elasticity of the string which is playing the role of the springs. Okay, and it's the inertia of the points which are at the antinode and near the antinode where the maximum kinetic energy occurs. Here it's concentrated on one particle. Here it's a little bit distributed between the two nodes, but the effect is the same. So that is how they have given an analogy between a system where inertia and elasticity is completely isolated. Spring is ideal, so its inertia hai nahi, mass is tending to zero, but it stores potential energy. Whereas the particles are like blobs. There are particular points at which the inertia is concentrated. Now that thing is happening in the standing wave on a string in a more distributed manner. Right, so that's an interesting analogy to understand this. Okay, now coming back to other modes. So the second case of standing wave we'll see is standing waves in a string with one end fixed, okay, and the other end flexible. Now this is also a very interesting case. We have a situation like this. Excuse me. So have that kind of thing. This is a ring going around a smooth pole. Fixed pole. And here you have a fixed end. So this becomes a flexible boundary, this becomes a rigid boundary. So x equal to 0, for example, becomes a rigid boundary. And x equal to L becomes a flexible boundary. So in such a case, the fundamental mode of vibration will look like this. The fundamental mode the string will vibrate like this. So this length will actually become lambda by 4 in the fundamental mode. Because this will be consecutive antinode and node. Okay, so lambda naught for the fundamental node will become 4L. So the fundamental frequency will be given by the formula 1 by 4L square root T by N. Whereas on the other hand, the first overtone for such a system would now look like this. First overtone mode would look like this. So the length of the string would become lambda by 2 plus lambda by 4. So you would see it would become an odd harmonic. In the first overtone mode, lambda 1 would become 4L by 3 because half plus 1 by 4, that is 3 by 4 lambda 1 would be equal to L. Okay. So that means the frequency would become 3 by 4L square root T by V. So most importantly, the frequency will become the first overtone's frequency will become the third harmonic of the fundamental. That means this is not capable of vibrating at the second harmonic. It can vibrate. So for example, if this is 10 hertz, now the next frequency at which this can vibrate is 30 hertz. It cannot vibrate at 20 hertz. So like that, the second overtone would now look like this. You get 2.5 loops. Look like this. So this is lambda by 2, lambda by 2, lambda by 4. So you would have 5 lambda by 4 is equal to L, or so the frequency would become fifth harmonic of the fundamental. So like that, the nth overtone mode would be such that n lambda by 2 plus lambda by 4 would become the length. As you can see in the fundamental mode, quarter wavelength is equal to lambda L. In the first overtone, it is lambda by 2 plus lambda by 4. Second overtone, it was 2 times lambda by 2. So like that, nth overtone mode, it becomes n loops plus half a loop in the end. Okay, so n and a half loops like that. So your lambda becomes 4L upon 2n plus 1, or your frequency becomes 2n plus 1 by 4L square root T by V. So such a system is one where only odd harmonics exist. So end of the day, what we understand is that for a string with one end as fixed and other end flexible, only the odd harmonics exist. So it's modal series, modal or harmonic series are such that so 1 by 4L square root T by V, my mistake. like that the series is nth overtone is given by this formula. So again, it's very important, you should not confuse between the term overtone and harmonic. Now, overtone is just like the index given to the frequencies. The fundamental is given the index 0. The first overtone is the next higher frequency. The second overtone is the next higher frequency. But harmonic is the multiple that you multiply, the number that you multiply the fundamental with. So that in this case becomes only odd multiples. So the formula becomes that the nth overtone is given by this. So I'll just minimize this and take you through the top again. But I think it's pretty easy to understand. So basically what is happening, because the free end of the string, the flexible end, is the pole is not offering any resistance at all because it's frictionless. So it has to vibrate in such a way that that point becomes an antinode. Now the maximum displacement has to occur at the free end. So it has that boundary condition that it has to be having the maximum amplitude, whereas the fixed end has to have zero amplitude. So it has to be a node. So the only possible harmonics it supports, this system, it naturally supports. If you create a pulse and that pulse is going back and forth, and the multiple superpositions are creating a standing wave pattern, that standing wave pattern has to be such that one end is a fixed end or a node, and the other flexible end has to be an antinode. So that is possible only for these frequencies. So again, were you to pluck a string like this, it would vibrate and create sound such that it would be a complex superposition of all these frequencies. Whereas if you want to create resonance by bringing a tuning fork near such a string, that tuning fork's frequency has to match one of these frequencies, the fundamental or any of the overtones. Okay, so hope this concept is clear. Okay. Now, so we are more or less done, but just one more interesting type of problem we'll discuss. So any doubt with this part? Odd harmonics क्यों होता है? This is clear, right, to all of you? Okay. Now, one more interesting type of situation can be created where we have not only the two boundaries, but we have some in-between point also where some complexity is being created. Like, for example, suppose we have this situation, we have a wall, and in that wall there's a very narrow aperture. Okay. And our string is going through that narrow aperture. So suppose we have this situation, and let's say that this is a fixed point, whereas okay, so imagine this is actually very close. So this is a thin wall with a very narrow aperture, with a very narrow opening. through which the string is going, and at the other end of the string, let's say it is attached to this kind of thing. A ring going around a smooth pole. Now let's say it has some tension T and linear mass density mu, and this is, let us say, 4L, whereas this is 3L. The total length of the string is 7L. Now we have to find the formula for the fundamental frequency of vibration. Okay. In terms of L, P and mu, and the nth overtone. So this particular string can vibrate in what fundamental frequency and what kind of overtones. So now you can see that where the aperture is present, it's a very narrow aperture, so the displacement is negligible. So this point will be forced to be a node. So what is happening is, if I label these points as A, B, but also this in between point C, you'll have to see, you'll understand that A will be a node, B will be an antinode, but C will also be a node now. So it's like a 3 boundary problem. Instead of 2 boundaries, the system has to support 3 boundaries or 3 boundary conditions. And that's how we'll find the frequencies of the fundamental and the overtones. You're understanding the point here? So what will happen in this case is that A and C will be nodes, whereas B will be an antinode. So what condition this will give us, C, and what condition this will give us, let's understand. Okay. So this will give us a condition that the distance between AC, that is 4L, has to be the distance between nodes. So it has to be some integer times lambda by 2, where n is 1, 2, 3, etc. Whereas the distance between these two, which is 3L, will have to be some odd multiple of lambda by 4. So these are the only wavelengths which are possible. So from the series of wavelengths, we will get this. So you can see that equation 1 and equation 2, they are giving the information that lambda is equal to 8L upon n, which is equal to 12L divided by 2m minus 1. Okay. So that is giving us that n is to 2m minus 1. It has to be a series which is 2:3. Here also m is 1, 2, 3, so on, because I've taken 2m minus 1. If I had taken 2m plus 1, then m could have started from 0. Okay. So you will see that this series is such that the possible numbers which support this are 2, 3. Okay. Then if I took, so next if I take n equal to 4, then 2m minus 1 should become 6, okay, which is not possible. So I have to take the value of n next value as 6, so that this becomes 9. Okay. Then I have to take 10, so that this becomes 15, and so on and so forth. Okay, so the fundamental frequency will correspond to n being 2 or 2m minus 1 being 3. Okay. So that corresponds to lambda equal to how much? 2m. So that will now look like this. Lambda is 4l, is it? Okay. Yes, yes, correct. Okay, this is what it will correspond to. So for this, the frequency will become 1 by 4l square root t by. Now the first overtone here, that will correspond to n being 6 and 2m minus 1 being 9. Okay, so that means this side of the string, which is 4l, will accommodate how many loops? It will accommodate 3 loops. Four L by 3. Okay, so now this side will have to account. This will have to be the case. So 6 loops on this side. There'll have to be another one. Okay, so guys, just having some trouble with my internet, so we'll conclude the session here since there's another session at 11. But you can see in that problem that we just discussed, I'll send you the notes with the complete thing. So what will happen there is, again, only odd harmonics will exist. And the harmonic series will be such that, your number n for the left hand side, which is between the two fixed ends, will have that kind of series. It will be 2, 6, okay, 10 like that. The odd multiples of 2, n will be odd multiples of 2, whereas 2m minus 1 will become odd multiples of 3. So for the fundamental mode, what is happening on the right hand side, where you have the ring on one side and the wall on the other side, the fundamental mode will have 1.5 loops. The first overtone will have 2.5 loops. The second overtone will have 3.5 loops, and like that. And that's how the modal series will go. So these type of problems are the more tricky type of problems. Very rarely they come in IIT, but they can come in JEE Advanced, where along with the two boundaries, you have some other boundary condition for some in-between point also. So then the modal series becomes a little bit more complex. Okay. So with that, we conclude this session, and officially that way we have completed everything to discuss in transverse waves. We can now go ahead with sound waves. But of course, next lecture we might be discussing some more questions and doubts depending on how much people cover with the module questions for transverse waves, as well as H.C. Verma and D.C. Pandey, etc. You can try out any questions. In between in the week also, you can keep sending me questions. I'll help you out with that. But with this knowledge, you should be able to cover any and everything to do with transverse waves. I'll also send you a couple of videos about Fourier transformation, and you'll understand some interesting things about that. So that's it for you people today. Thanks for attending.